Hello, this is Wen Tao from Caltech. Today I'm going to present you the poster of our paper on secure level coding with Uniform Wiretap Sets. So I will first introduce you the problem. We assume there is a source S that wants to deliver a secret message M to the destination D under perfect strong or weak secrecy requirement. So all these are information theoretic secrecy requirement. We are assuming that any node in the network is allowed to generate independent randomness, which could be used as keys to protect the message. We also assume there is an eavesdropper in the network that can wiretap a subset of edges chosen from the collection of all wiretap sets. In this paper, we studied the uniform case. So the word uniform has two meanings. First, all edges are uniform and have unique capacity, and then all the wiretap sets are also uniform, so that the eavesdropper can wiretap Z arbitrary links. So this means it suffices for us to specify a number Z instead of the collection of all wiretap sets. So here is some existing results about secure level coding. The problem is thought to be well understood in the uniform setting. So Cai and Yan has shown that if only source can generate randomness, then the secrecy capacity is characterized by the cassette band. However, the problem is more difficult in the non-uniform setting, and Cui et al. Has shown that if either the link capacities or the wiretap sets are not uniform, then the secure level coding problem is NP hard. And Chan and Grant has shown that also under the non-uniform setting, if all nodes can generate randomness, then the secure multicast is at least as difficult as multiple unicast. As of our contribution, we first showed a hardest result. So we show that if all nodes can generate randomness, then a secure unicast, even in a simple uniform setting, is at least as difficult as a multiple unicast under all three kinds of secrecy constraint. So I would like to compare our results to previous ones. First, we show that the problem is difficult even under the uniform setting. So this is quite surprising because under exactly the same setting, except that only source can generate randomness, then Cai and Yan show that the capacity is just the min cut minus Z. However, if we allow randomness to be generated at other nodes, then suddenly the problem becomes much more difficult. Intuitively, this is because if only the source can generate randomness, then the wiretapper can always wiretap at the min cut, and therefore the capacity is min cut minus Z. However, if we allow randomness to be generated by intermediate nodes, then it could be the case that some randomness is generated downstream a cut, and there are some backward edges that send this randomness upstream. So these backward edges are not counted in the cut capacity. However, they are still helpful because the randomness they are transmitting can be used as keys. Okay, so the second difference is that we show that even a single unicast is difficult instead of a single source K multicast. And finally, our results applies to perfect, strong, and weak secrecy requirements, whereas previous works only study perfect secrecy. This paper also studies achievable strategies. I will mention that later. And let's first look at the hardness result. The idea is that we are trying to reduce a general multiple unicast to a single secure unicast under simple setup. Here goes the theorem. Given any unit rate K unicast problem, this K unicast problem is feasible if and only if the secure unicast problem join the picture with unique capacity links and one arbitrary wiretap link has secrecy capacity K under all three kinds of secrecy constraint. So we can see the source here, the destination is here, and there is a general network embedded here. So this single secure unicast may appear to be easy at the first sight because everything is uniform and there is only one wiretap link. However, we will show that this actually is equivalent to a multiple unicast problem. Okay, let's see why is that. So suppose the K unicast is feasible, then the scheme in the figure achieves secrecy rate K. So here Vx is the local key injected by node X and the M's are the messages. So the scheme is secure because every edge is protected by one local key, and the destination can decode because all these local keys cancelled either inside the network or at the destination. In particular, if you look at the k horizontal edges, such as this one or this one, then each of them can transmit 1 unit of message protected by a local key generated at, for example, here at B1. And because the multiple unicast is feasible, the same local key is also available at the node C1. And therefore, the local key can be cancelled and be replaced by a new local key generated at E1, and therefore the destination can decode. So also notice that the min cap from S to D is indeed K, therefore the capacity is K. Now let's look at the other direction. Suppose the secrecy capacity K is achieved. So let's go back to the figure. I will delete that. And now let's consider the set of edges C1, D1, E2 to EK, and F2 to FK. And this is a cut from S to D. But notice that by construction, all the F edges are independent from the message. And based on this, we can actually show that the edge C1 and D1 together must deliver 1 unit of information about the message. On the other hand, we also know that due to the secrecy constraint, every single edge in the network must be independent from the message. So based on this, we can further show that C1 and D1 are all filled up to capacity, and actually they are functions of each other given the message M. However, because we are trying to show the multiple unicast from this side to this side is feasible, we had better introduce the edge B1. And we can do this by noticing that C1 learns everything about D1 from B1. And therefore we have a Markov chain. So again, this is due to this Markov chain follows from our network construction, because by the network topology design, B1 is the only incoming edge to C1 that could be dependent on B1 on D1. And based on this Markov chain, we can show that we can decode D1 from B1, extending this argument to all other branches, and apply the general coding theorem. We'll show that the multiple unicast is feasible. Okay, now let's go to the achievable strategies. So even though we show the problem in general is very difficult, we are still able to find some efficient achievable strategies. And the first one is a generalized global key scheme. So a global key scheme, we use only global random keys that are decodable at both the source and the sink. And comparing to existing works, our strategy has the advantages that we allow these keys to be generated anywhere in the network. And I guess I don't have time to cover this needed program in details, but the idea is that because it requires the keys to be decodable at both the source and the sink, therefore we can reduce the problem to a multi-source multicast problem, and the capacity of this multi-source multicast problem is well understood, and therefore we can formulate it as an LP. And let's look at an example. So in this example, we have 3 wiretap links, and the scheme achieves unit message rate. We can see that the message M is indeed secure because it is protected by 3 global keys. And it is interesting to notice that our LP is actually quite smart in finding solutions that allowed multicast coding of keys. For example, our solution here actually is taking advantage of the butterfly network to multicast keys. Finally, let's take a look at the local key enhancement algorithm. I guess I only have time to do a quick example. So let's say we have a network with 2 wiretap links. And in order to apply the local key enhancement algorithm, we will first start with a global key solution. So for example, this solution, in this global key solution, we can achieve message rate 1. And in particular, we have 3 paths from S to D, and 2 of them are used to send keys, K1 and K2. Only 1 of them are used to send the message M. Now we want to improve the rate by 1. So we want 2 of these paths to be sent to send messages, and only 1 to send keys. And because we will be sending 1 less global key, in order to maintain the secrecy constraint, we will lead these 2 message paths to be protected by local keychain. And a local keychain is composed by local key gadget. In general, there are 3 kinds of local key gadgets here. In this example, they are drawn in blue. So the local key gadget can be either a forward path like this, SA, or a backward path like this, ES, or a combination of 2 paths like this, BA, BD. So if we transmit a local key on this gadget, then this gadget can protect the message path they covered. So these gadgets can actually overlap. For example, the gadget BD, BC is overlapping with the gadget ES. And this gadget can also share edges. For example, the gadget BA-BD protecting the central path is sharing one edge BD with the gadget BD-BC protecting the right path. So our algorithm is efficient in searching these local key gadgets and therefore improve the rate. So if we compare these two schemes, then notice that now we are no longer sending the key K2. Instead, we are sending a message M2 here. And the role of K2 is replaced by local keys V1, V2, and V3. Okay, so this is all of my poster talk. Thanks for watching.